This is the 9th electromagnetism video for A-level physics. The aim of this video is to use Faraday's law to understand the graphs of flux linkage and voltage against time. And more importantly, how those graphs actually relate to each other. Again, we'll be looking at Faraday's law. So first we should try to plot out a flux linkage against time graph. To do that, we'll need an equation for flux linkage in terms of time. Previously, we've seen for a rotating coil that n phi is equal to nba cos omega t. Right? Often we write cos theta, but we established in the last video that we should write omega t. Let's sketch this graph out. So we've got time on the horizontal axis, and then we've got flux linkage n phi on the vertical axis. Well, this follows the cos graph, and it's just scaled by NBA, so its magnitude is NBA, and as its cos, it's going to start at its amplitude, it's going to start high, and then follow the sinusoidal shape, so like so. Then at its lowest point, the flux linkage will be minus NBA. That just means the flux is directed the other way through the loop, from the loop's perspective. At this stage here, the loop will have gone through a quarter turn. Here, the loop will have gone through a half turn. Here, 3/4. And there, 1 full rotation. Okay. To use this graph, though, and come up with the graph of EMF against time, we need to consult Faraday's law. So Faraday's law tells us that the rate of change of magnetic flux linkage is equal to the EMF. Well, the rate of change of flux linkage against time is just going to be the gradient of the graph we've got currently. So let's mark some tangents on here and just see how the gradient changes as we go. These will be marked in yellow. So then we're at this point down here, it's 0. Here, it's large and positive. There, it's 0 again. Here it's large and negative, and then there it's 0. And that pattern just goes on and on. So we'll note those points. We've got 0 at first, then we've got large and negative, then we've got 0 again, and we've got large and positive. And this pattern just repeats itself over and over again, 0, and then large and negative. As in, those two go together, right? You can see the gradient is negative there, and it's very substantial, it's very steep. Here, this 0 goes with that 0 there, the gradient is 0. So let's try to plot a graph that captures that information. 0, large and negative, 0, large and positive, 0, large and negative, and just keeps going through that pattern. So it starts at 0, we'll dot the origin, and we believe this is going to be the graph of EMF, right? We used Faraday's law to come up with this. Then it goes to large and negative, so it drops down at first, and then it goes to 0 again, and then it goes to large and positive, so it's up high, and then it's back to 0 there, and then it's large and negative. And this pattern continues, so we'd have 0, large and positive, 0, large and negative. Well, the graph we know that will stitch this together is the minus sign graph, which looks like that, roughly. Now something looks a little bit wrong here, because in the last video we established that EMF is equal to omega nba sine omega t. But what we've got here looks like a minus sine graph. The reason is that Faraday's law, as we stated it, we haven't factored in Lenz's law and got rid of the minus sign. So what we have to do is actually we have to invert all of the signs when we go through and look at the gradients. So here we used to have large and negative. Really, we should have large and positive on our graph. And here we had large and positive because we have our minus sign, or we're supposed to. Positive becomes negative. And again over here, where it was negative, it should be positive. So we'll sketch that out. So we've flipped the arrangement now. Just do a very quick sketch. The zeros all stay the same, right? If you multiply 0 by -1, nothing budges. But points like this, where the value is large and negative, become large and positive. And points like this, where it was large and positive, it becomes large and negative, right? Large, negative value, and so on. And now we've got the sinusoid that we see in the properly derived equation right there. We can flesh out some more detail because here we've really just focused on key points, right? Just to again circle those, like there, 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 there. We've just used key points, so we haven't quite justified the shape that it's sinusoidal. Right? We could have said, oh, it should be connected like this with some kind of triangular looking graph, but we can go a bit further to justify this. So we'll put down the flux linkage against time graph, and then right below we'll put the EMF against time graph, and these two are a corresponding pair. So we'll put down the cos graph that we're familiar with, like that. And we'll look at some other points in between, but we'll just get down the key points. So we know that we're looking at 0 gradient at first, right? It's flat. Then we're looking at a large negative gradient, but remember we have to change the sign. So at that point there, we actually have a large positive value. And then we kind of know what the pattern is like. Back to 0, 0 gradient. Large and positive means large and negative. And then we'll just add in those key points. Okay, but we're looking at sections like this. We want to know about the shape there, or sections like this. So let's focus on a particular section of the graph. Let's focus on this bit here in red, and we'll see how the gradient changes. So the gradient, it's steep and positive at first, right at that point there. At this point here, it's not quite as steep, still pretty steep. By that point there, it's really nowhere near as steep. There, there's no gradient at all. At this point, there is some gradient, but it's directed down and it's not particularly steep. Then here we've got a steep negative gradient, and then finally there we've got the steepest negative gradient. So we can see the gradient changes gradually, and remember gradient is rate of change. So the rate of change of flux linkage with respect to time is changing on a continuous basis. It's not a fixed gradient, so we need to also have a smooth, continuously changing curve in the corresponding graph below, as in the EMF needs to change in the same smooth fashion. It needs to be curved as well, so it's going to come up like this and around over like that. We can just look at one other issue with this. Let's compare two flux linkage graphs to each other. So let's say that we've got flux linkage against time, and in one case it changes very, very slowly. So let's say it looks like that. It rises very slowly, and then on the other side it falls very slowly. The rate of change of flux linkage isn't very significant. And then we'll draw sort of the opposite of that, or a very different situation. We'll say we have one where the flux linkage changes by a lot in a really small amount of time. So big change in flux linkage in a small time. So that's a high rate of change. So we're expecting a large EMF to be induced. So we'll look at EMF against time. It's only going to generate EMF for a short time because the flux linkage only changed for a short time, right? That short span just marked there. So in this case, it's very, very steep. Right? Draw all of the gradients we're going to draw on here. They're very significant. You know, whether they're negative or positive, they're all pretty large, except for the one at the very top. I just need to move that axis so we can get some negative values as well. So at first, the gradient is large and positive, so we need a large negative value to start. And then by the time we're halfway through, the gradient is 0. And then by the end, around here, the gradient is large and negative, so our EMF will be large and positive. So it will look like this, a very steep sinusoid. Okay, and then if we look at the other one, the one that changes very slowly, it's going to have much the same shape, but over a much greater span of time. Right, this one spans that red span of time, so the one here also spans that red span of time. And the axes are labelled EMF and time. The gradient here is positive, but it's not particularly significant, it's not very steep. Here it's 0, and on the other side it's negative, but not particularly steep. So a small positive gradient means we get a small positive value for EMF, so a small negative value for EMF. It's 0 right in the center, the gradient, so the rate of change of flux is 0, so EMF is 0. And finally, that's small and negative there, so the rate of so the EMF is going to be small and positive. Again, it's got to look sinusoidal, so it's going to look like this. So you can see the difference between these two. This one on the right, where there's a rapid change of flux linkage, right, big change of flux linkage in a small time. It's very steep. It generates a large EMF. Down there it's large as well. This one here on the right, the EMF induced is small. Small EMF. That's small because the flux linkage didn't change very much and it took a long time to do it. So the rate of change of flux linkage is small.